In the world of nuclear physics, certain atoms possess unstable nuclei. These atoms spontaneously emit radiation to reach a more stable state. This process, known as radioactive decay, occurs randomly for individual atoms but follows a predictable pattern for large populations. The rate at which a sample decays is directly proportional to the number of radioactive nuclei present. If you have more atoms, more will decay per second. This fundamental observation leads us to a precise mathematical law governing nuclear stability. We introduce the decay constant, lambda, which represents the probability of decay per unit time. The negative sign in our equation signifies that the number of radioactive nuclei, n, is decreasing as time progresses. This is the starting point for our derivation. To find how the number of nuclei changes over time, we rearrange our differential equation to separate the variables n and t. By integrating both sides from the initial state at time 0 to a future state at time t, we can solve for n. The integral of 1 over n results in the natural logarithm of n. By applying our limits and using the properties of logarithms, we simplify the expression. We are now just one step away from the exponential form of the decay law. By taking the exponential of both sides, we arrive at the radioactive decay law. This equation tells us that the number of parent nuclei decreases exponentially over time. The rate of loss slows down as fewer radioactive atoms remain. To find the relationship between the decay constant and half-life, we substitute n with half of n0 into our decay law. We can immediately cancel out the initial quantity, showing that half-life is independent of the starting amount. We take the natural logarithm of both sides to isolate the time variable. Since the natural log of 1/2 is the negative of the natural log of 2, the negative signs on both sides of our equation will cancel out. This gives us the final elegant relationship. The half-life is equal to the natural log of 2 divided by the decay constant. This allows scientists to calculate how long a substance remains hazardous or to date ancient materials. Let's apply this to carbon-14, used in radiocarbon dating. Given its decay constant, we divide 0.693 by 1.21 times 10 to the negative fourth. This calculation reveals the duration of one carbon-14 half-life. The result is approximately 5,730 years. After this period, half the carbon-14 is gone. After another 5,730 years, only 1/4 of the original amount remains. We can also calculate the activity, which is the number of decays per second. By multiplying the decay constant by the total number of atoms, we find the activity in becquerels. This tells us the current strength of the radiation source. Often, the daughter nucleus produced by decay is also unstable, leading to a decay chain. Each step in this series has its own unique decay constant and half-life, continuing until a stable isotope, like lead, is finally reached. A helpful shortcut is the power of 2 rule. After n half-lives, the fraction of the original sample remaining is always 1 over 2 to the power of ln. This makes quick estimations very easy during lab work or exams. To summarize, radioactive decay is a statistical process resulting in an exponential decrease of nuclei. The half-life is a fixed property of an isotope, inversely proportional to its decay constant. These laws allow us to predict the behavior of radioactive materials over vast timescales. Think about this: if a sample has a half-life of 10 minutes, what fraction remains after 30 minutes? Since 30 minutes is exactly 3 half-lives, we calculate 1/2 cubed. The correct answer is 1/8. Generated by Vision Solve AI.